Hi, my name is Ivan Ruchkin. I'm a postdoc at the University of Pennsylvania, and today I want to tell you about confidence composition for monitors of verification assumptions. Before we move on with the presentation, let me draw your attention to the top of this slide. You can see the blue thing, and you can be pretty confident that this is a Lego block. You can see the things to the right, and maybe you're less confident that these are Lego blocks. So one question is, if you were to compose the blue and the red things, how confident would you be that you get just a bigger Lego block? That's an intuitive version of the question underlying this paper, confidence composition, which I will now explain. Let's start with a motivating scenario. Think of the unmanned underwater vehicle, or UUV. This is basically an autonomous torpedo that has to scan the blue pipeline for cracks and also avoid obstacles represented here with this gray box. Obstacles like fish, ships, debris, and others. As you can see in this video, the neural network controller fails to avoid this obstacle and crashes. And that's the kind of failures that we would like to anticipate. To perform its mission, the system is sensing the distance to the obstacles and the position with respect to the pipe. But it also has confidences in detecting the obstacles in the pipe and also in its ability to control itself using its fins. So the goal here would be to combine the runtime confidences into a single predictive probability of safety. And this goal doesn't just happen in the UUV, it applies to many other autonomous cyber-physical systems with a lot of uncertainty. Some relevant works come to mind. For example, there's a lot of literature on aggregating predictions of the same phenomenon. You can think of ensemble learning, for example. The difference here is that we are tracking different phenomena. We're interested in obstacles, the pipe, the dynamics, and so on. So the typical setting of the mixture of experts doesn't mathematically match our setting here. Another idea is constructing a comprehensive model that would relate all the confidences and the distances and the safety outcomes to each other. For example, you could train a Bayesian network to predict safety here. The key issue with the comprehensive models is that to make them, you need to commit to some dependency model between the confidences. And if you think about it, confidences themselves are second-order, highly uncertain quantities, and it's difficult to pretend that we can figure out how dependent they are. At least it's easier to figure out the original question of the probability of safety than the dependencies of confidences. So if we want the guarantees, comprehensive models aren't necessarily the best choice. In this paper, we investigated an alternative approach that I want to share with you. In the rest of this presentation, I'll talk about the key ideas behind that approach, verification assumptions, and confidence monitors. I'll give you an overview of the CoCo framework that we use to predict safety probability. And I'll particularly zoom in on a couple of contributions, the theoretical calibration bounds and the experimental results for the UUV system that I showed. So let's get into it, and let me explain why we even need these key concepts in this scenario. So suppose you're building this UUV system, and you have a couple of things. You have a simulator of that vehicle and the sensor data from the real vehicle. So one thing you can do is train a control neural network using reinforcement learning in that simulator. Of course, we want to know how safe this controller is, so we'll create a dynamical model that describes how the system and the environment move, and plug it in along with the controller into one of the state-of-the-art approaches for safety analysis. It's called closed-loop neural network verification. Essentially, it's a reachability analysis that composes the dynamics in the controller and explores if it's possible to violate safety, which means failing to avoid obstacles or losing the sight of the pipe for the case of the underwater vehicle. If our controller is good, the safety verification will give us the verdict safe. That means it's impossible to violate safety properties using this controller. That's a great property that we want to have and a strong guarantee. But we also need to handle sensing data. So let's train a perception neural network that would detect obstacles and pipes around the vehicle. These neural networks would be deployed at runtime in the vehicle itself. And we don't trust them at runtime. So along with them, we will deploy confidence monitors. Confidence monitors quantify how much we trust that the networks are doing a good job, that they are producing the right outputs. You can think of the logits in the softmax layer as one kind of confidences. And so in this setting, you may start being able to see why it is so difficult to quantify safety. It is because the safety guarantees and the confidence monitors don't have an obvious relationship with each other. For example, if we have an 80% confidence in the control action, doesn't mean that we are 80% safe. Or if this confidence monitor says 80% and this one says 50%, which one do we trust and how do we combine them? So in this setting, it's not clear. So let me redraw this picture a bit and try to clean it up using the idea of verification assumptions. So instead of generating confidence monitors right away, let's encode the information from the simulation and sensor data in our verification model as assumptions. For example, you can encode assumptions about what the obstacles would do from the simulator, or an assumption on the upper limits of the sensing errors from the sensing data. And then under these assumptions, we will try to verify the system and hopefully get the safety verdict. Now we can generate the monitors for the assumptions themselves, and the monitors will tell us at runtime how valid the assumptions are. This has a couple of advantages. One is the sufficiency for safety. If the monitors tell us that we're okay, then we are indeed okay, because that's exactly the analysis we did at design time. Second advantage is that we get an explicit relationship, desired relationship between assumptions. For example, you may have to assume for verification purposes that both assumptions hold from now on onwards. And this naturally translates into a relationship between the monitors. This means that now we want both monitors to tell us that assumptions hold at all point in time. Okay, so this cleans up the picture and helps us relate the monitors and the safety guarantees. I want to say a couple of words about how we can monitor these assumptions. There are several options there. The typical approaches have discrete outputs such as yes, the assumption holds, no, it doesn't hold, or maybe, we don't know. There are well-developed theories for this kind of monitoring, but they are not ideal in our situation. One issue is that these outputs are not granular enough. If you have a highly uncertain assumption, for example, some kind of statistical independence, your monitor may not have enough data, and then it will just tell you maybe, 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 maybe. That's not very useful or actionable. Another issue is the combinatorial accumulation of errors, and we actually ran into this in our recent work on composing discrete output monitors. If each monitor has some false positive, false negative rate, adding a lot of them into a composition creates a lot of errors and makes the whole monitor infrastructure less useful. So let's instead consider the idea of confidence monitoring that we saw in the neural networks and apply it to monitoring assumptions. Here I want to give you a couple of definitions. So confidence is a specific technical term that means an estimate of the marginal probability of some assumption. And the assumption is a random binary variable here. Confidences are estimates, so not all estimates are equally good. And we will measure how good they are using a standard metric for machine learning called expected calibration error, or ECE. And it is defined for some confidence C with respect to assumption A as an expected value of the absolute difference between the predicted probability, or confidence C, and the actual frequency of the assumption holding when these predictions are being made. For example, if a monitor tells us that it's 80% confident in an assumption, and we repeat such situations, and only in 70% of them the assumption actually holds, that gives us the ECE of 10%. And the best ECE is 0%, that's called perfect calibration. So we'll use these concepts to monitor our assumptions. Okay, so now we're ready to go ahead and look at how we combine these monitors to get a single confidence in our safety guarantees. And this is what the CoCo framework is for. That's the framework that we recently designed at the University of Pennsylvania. I'll explain it on this overview slide. On the right-hand side, we'll have the runtime online executing part of the systems. And on the left-hand side, we'll have design time artifacts. So let's start with some safety property. For example, this one says that we keep a reasonably safe distance from obstacles. And when the obstacles are really far away, we are well positioned to scan the pipeline. So this prioritizes obstacle avoidance over pipeline scanning. And suppose we have a controller, a model, and so on, that we will try to verify using this closed loop neural network verification. This is difficult to do because the model is uncertain and open-ended, and we need to constrain it. This is where the assumptions come in. We'll make a couple of assumptions on the environment that parallel some parts of the specification. For the dynamics, we'll assume that we don't know the real dynamics of the system, but we know it up to some epsilon. For the perception, again, we don't assume perfect perception, but we'll assume some bound on the perception error. Now is an important step. A human needs to combine these assumptions. In this work, that means writing a propositional logical formula over them. And this formula encodes the situation, the scenario, under which we're trying to verify the system. And hopefully, if our controller is good in that scenario, we will get the safety verdict. That's great, and that's what we want to have at design time. The only remaining question is the validity of assumptions. And this has to be resolved at runtime. So we can create confidence monitors for each assumption. And this can be done using state-of-the-art methods, nothing particularly new here. We deploy these monitors in the system at runtime. At each point of time, the monitors give us the respective confidences in their assumptions between 0 and 1. Then we need to compose these confidences using some function f and get the overall confidence c. And if we do this well, our overall confidence c is going to quantify the confidence in the safety guarantees that we obtained at design time. And this confidence is a conservative proxy for the confidence in safety itself, which is what we wanted to begin with. So this is the overview of the framework. You can see how it combines heavyweight, computationally intensive analysis at design time with lightweight composition at runtime. The key to making this framework work is composing the confidences appropriately. And so I want to spend a bit more time explaining the mathematical aspects of how to do that. Let me clean up this picture. So we have our composed confidence, and it's supposed to predict the safety outcome, which is a binary random variable. It either happens, we're safe, or it doesn't happen, we crash. We want a good enough estimate of the probability of the safety. That means that the ECE needs to have some known upper bound E that's hopefully small and not 1. So this is difficult to do because, as I said before, we don't know the dependencies between monitors, and monitors don't give us the exact true underlying probabilities. They give us approximations with errors. So it's difficult to go directly from composed confidence to safety outcomes. Instead, we'll go indirectly. Remember that for each monitor, there is an underlying assumption that's being monitored. And what we can do is use state-of-the-art AI techniques to calibrate the monitor to its respective assumption and obtain the individual bounds on those calibrations. Then remember that we also have the combined assumptions, A, under which we verified the system. So we know this relationship between A and S. It's partially probabilistic, partially deterministic, and we learn it by doing this heavyweight design time verification analysis. So now we can start seeing the possible simplification here. Instead of going directly for safety, we will try to use C to predict our combined assumptions, and then use this verification relation to get at safety. And in this paper, we have a theorem that enables that. It says that we will get our goal calibration if we manage to calibrate our C to the assumptions with a bound that is related to the original bound we wanted. So this is very useful because now we can forget about the safety for a moment and just focus on predicting the combined assumptions. Technically, we're asking, what's the probability of a propositional formula holding if we know the imprecise probabilities of every proposition? And this is a complicated problem with several moving parts. One of them is logical manipulation. Another is the underlying dependencies between assumptions. But in this paper, we managed to boil down this question to the problem of conjunctive composition of calibration errors. And this is the first time the problem is posed in this form. Let me explain it. Suppose we have two monitors and they're calibrated to their respective assumptions with known bounds. So now to compose them, we need to find some composition function f and the associated bound ef such that the functional composition of the two monitors is calibrated to the conjunction of assumptions with that bound ef. You can see here that there's an interplay between continuous composition of probabilities and the discrete logical composition of the underlying assumptions. We haven't fully solved this problem, but we made good steps towards the solution. We took a couple of functional families in place of f and investigated what kind of bounds we can get. And these functional families can be just used directly without any extra data. These families are multiplicative confidence and the weighted average of confidences. And here are the bounds. The details are not important. What is important is that we get known guaranteed calibration bounds for such compositions. If we have some data from the joint distribution of monitors and assumptions, we can try to use the data-driven approaches for F, like logistic regression and Bayesian estimation. In this case, we don't get any bounds, but if we have good enough data, we would probably get better performance out of the data-driven approaches. Either way, either theoretically or empirically, we managed to satisfy the precondition of this theorem, which ultimately results in getting a calibration bound on the safety probability. So, long story short, without assuming perfect monitoring or knowing the dependencies between monitors, we managed to obtain a bound on how well we know whether we will crash or not. So that's all the math I wanted to show you. Let's move on and see how all this works in practice. Is this useful? To answer this question, we completed a number of experiments in the rich and complex UUV simulator. And during these experiments, we perturbed the underlying assumption behind the system. Sometimes these perturbations resulted in safety violations. And so it turned out, as a result of these experiments, that our composed confidence that our framework produces, outperforms the confidences of individual monitors when it comes to predicting safety. And this is good, and this is what you would expect from any good compositional method. Here I want to show you this plot. I'm showing ECEs, so smaller is better. We have a couple of monitors we're composing. You can see that the first monitor performs better than the second one. And then there's a couple of ways to compose them. One is using the functional forms, and you can see that this one works as well as the best monitor, which is already good because we didn't know which monitor to trust. And then there is the data-driven approach that can outperform all the monitors and non-data-driven compositions, further improving the calibration. So that's good. And there's another case study in the paper on a mountain car. I'm not talking about it now, but the results are similar there. And all of that confirms indirectly our theory because all these calibration errors fall within the bounds predicted by the theory. All right, so that's all with the contributions. But one thing I really like about this paper is that it opens a lot of interesting questions. One direction for the future work is making the confidence composition more algorithmic and systematic. There's a lot of things that the human needs to do now that can be done automatically. For example, finding suitable assumptions and synthesizing confidence monitors is an interesting direction. Also, we could compose confidences not just for small formulas with conjunctions, but for arbitrary propositional formulas over an arbitrary number of assumptions, using logical reasoning for that. Also, we can take a family of composition function and try to find the one that minimizes the calibration error for composition. So that's another algorithmic work that is possible. There are also some limitations to the current work. The confidence is not exactly accurate. It's often very pessimistic because we're trying to take the worst case probability of safety. It can be made more optimistic by incorporating more data that would give it the cause for optimism. So we can take all the testing data for the controllers, simulation data for the system, and we can also validate the models that we use in these predictions by using observations that we get online. All of that can improve our confidence estimates, make them more optimistic and accurate. Finally, once we get really good confidence estimates, we can inform recovery and control using them, and hopefully get some probabilistic guarantees on safety, even when something breaks in the system. So these are the future directions. Let me now conclude the talk. I told you about the CoCo framework for composing confidences and verification assumptions of autonomous cyber-physical systems. In this paper, we derived the first bounds of the kind that I showed for calibration errors. And we also showed that the composed confidence is a useful predictor of runtime safety based on the 2 case studies. The data is available on my GitHub, and thank you for listening.